everybody for joining us for Refrigeration 201. This is Advanced Refrigeration. We're going to go through this just like we did Refrigeration 101. Hopefully cover it over a 3-day time span. And with that, I'm going to turn it over to Kevin McClanahan.
Good morning, everybody. I hope you enjoyed getting to know the people in your house a little better this weekend, and kind of strange times these days, but I'm glad you're all here. They call it advanced refrigeration. This is just the next step above what we did with basic refrigeration last week. It's got some of the same content because some people didn't go to 101; they just go to 201. So there is some repetition, but other than that, it's actually a pretty good class. I always show this picture just because I just love this guy's duct work. It's great. So of course you can see him. He's up over here. Let's see, laser pointer. Yeah, he's up over here sitting there in his underwear with the box fan blowing on him. But that's drawing the cold air out of your freezer and turning it into air conditioning for you. That's all pretty good. So what breaks on a refrigeration system? I asked the class, and basically everything can break on a refrigeration system. Most commonly, it's a compressor or an expansion valve, depending on what's going on there with the contractor. But what causes these compressor failures? There's either mechanical failures or electrical failures. The diagnosis that your contractor does is the key to how that all comes about. As a counter person, normally you're not called on to do troubleshooting for a guy. He's the doctor. He's the one who's doing the work, so he should know how it failed. And there's a variety of ways that they do that. And when you're talking about compressor failures, there's in essence about 5 modes, or maybe 6, but these are the most common modes of failure in a compressor, and as far as mechanical failures are concerned. Refrigerant floodback, that's an issue where you've got liquid refrigerant coming back to the compressor, diluting the oil in the crankcase of the compressor. And in some cases, when it's strong enough, a strong enough flow of liquid refrigerant coming back, it can actually break the compression portion of the compressor, like the scroll or the pistons, rods, things like that. Flooded starts is when you have migration in the off cycle, when liquid refrigerant has an affinity for the oil in the system, and the liquid refrigerant comes back to the crankcase of the compressor and condenses there and causes a flooded start. That flooded start can do a variety of different things. If it's violent enough, if there's enough liquid refrigerant in there, if it's violent enough, it's going to throw that liquid refrigerant up on the bearing surfaces. And liquid refrigerant and bearing surfaces don't match up very well. So you get an uneven wear pattern when you do a tear down on something like that. Then slugging. Slugging is pretty much from refrigerant floodback, but slugging is more along the lines of having oil coming back. That, for instance, you go out to a job site and you find an empty gallon jug of refrigerant oil sitting by the system, and you wonder, well, where did the other oil go? So it's laying out in that system waiting for the proper opportunity to come flying back, and not paying attention to anything except for the level of the oil in the sight glass that could have a frozen up expansion valve or evaporator, something like that that's making the oil stay out in the system. And then when it does finally get broke free, goes through a defrost, something like that, that oil comes flying back, and that can break things just like a refrigerant floodback would. High discharge temperatures. When you have superheat coming back to the compressor, sometimes they say 20 degrees at the compressor. Heatcraft, I think, sometimes says 30 degrees, depending on the compressor. That's translated into the higher discharge temperatures. When you increase the superheat coming back to the compressor, it increases the superheat leaving the compressor. And high discharge temperatures have a tendency to cook oil if they're hot enough, 325 degrees or so at the valve port. But what that does is it creates carbon, and that carbon flowing along with the refrigerant oil and the refrigerant comes around to the bearing surfaces, and it's abrasive and causes issues with bearings again. And then loss of oil, like I said, the slugging portion, losing oil. If you don't find an oil slick on the floor, it's still in the refrigeration system. It's someplace out there and it's been trapped, and it needs to get loose and come back before you add more oil. So those are the 5 mechanical failures on a compressor. There's also electrical failures that occur, short to ground, winding insulation breakdown. Short to ground is pretty easy. You check the case of the compressor against the windings, the winding terminals, and if you've got continuity there, then that's an issue. Insulation breakdown, turn-to-turn shorts, that kind of thing, from POE oil or acidic conditions that haven't been addressed in the refrigeration system from, say, a burnout, that kind of thing. Can attack the windings and degrade the insulation on the windings. And if that occurs, then that's going to be a problem. Also, when you have a center on a semi-hermetic compressor, when you have a center bearing wear, if you allow that rotor to dip down to the stator, it can impact the stator and create winding insulation breakdown. And basically do that turn-to-turn short. No failure at all. About 30% of the compressors that come back to us had no defects, and that's there's a variety of reasons that could have happened, but that's a very high number, 3 out of 10 that have no problems at all. So, looking at this class, we're going to go through electrical fundamentals somewhat, installation and maintenance basics, the piping, wiring. Ed's going to talk about the sizing. We'll talk about defrost and charging. And we don't have exactly a diagnosis section, but the system diagnosis is going to be mixed all the way through this class. So you're going to see that come up several times during the course of the 3 days. So. Capturing conditions. If you've got a PT chart, you can follow along. Since I don't have the capability of interaction with you guys, I've got a PT chart in front of me, and I'm going to take some measurements on this refrigeration system here. From the compressor, right over here, this is going backwards from the refrigeration system we used yesterday or Friday. It's actually going counterclockwise this direction. So it goes through the condenser, goes to the receiver, out the liquid line up to the expansion device, through the evaporator, and down the suction line to the compressor. And every one of these gauges has a poundage attached to it. We'll just change that over so it has the poundage. And we'll take some readings on this and see what's going on. It has a measured temperature, so you can actually see what's going on as far as the temperature is concerned, and see where there's subcooling. You can see where there's superheat. You can see saturation, that kind of thing, because these numbers applied against the data. So let's look at the compressor here. It's 260 pounds of R22. 260 pounds is 120 degrees. And the measured temperature is 210. So let's see if it's 120. I would say it's superheated, because the measured temperature is 210, right? Okay, so we get up here, measured temperature is 120 degrees. And we already know that 260 is 120 degrees, so we could say that since the temperature and the pressure relation are the same, that's saturated. So saturated condition in the condenser there. Coming down to the receiver. Receiver's 243, so what's 243? That's about 115 degrees. And the measured temperature is 115 degrees. So that means that we've got saturation in the receiver. But that saturation is only on the top skin of that liquid that's in the receiver. Below that, where this dip tube from the receiver pulls its liquid refrigerant from, again, we're 115 degrees here, but the measured temperature is 110. So we're actually 5 degrees of subcooled liquid laying underneath that skin in the receiver. So that transfers up the liquid line at 110 degrees, and it's 5 degrees of subcooling. So it gets up here at 226 pounds. 226 pounds is 110 degrees. The measured temperature is 102, so we've got 8 degrees of subcooling at this point, at the expansion valve inlet. So we had 5 degrees of subcooling here, now we've got 8 degrees of subcooling there. I ask, why would that be so? Well, you got to figure that it's 100 degrees in temperature, and if it's passing through a 60-degree space, an ambient space that's 60, 70 degrees, it's actually hotter than the ambient, and it's going to reject heat to the ambient. Okay, so we go through the expansion device. We get up to the measured temperature of 41 and 70 pounds. 70 pounds is right about 41 degrees. So we've got saturation in here in the evaporator where we have liquid and vapor together, boiling off. Then we get to the outlet at 49 degrees and it's 67 pounds. 67 pounds is about 39, and the measured temperature is 49, so we've got 10 degrees of superheat at this point. Okay, so we had our discharge temperature going through here, through the condenser, saturation, down to the receiver, saturation, 5 degrees of subcooling coming up the liquid line, 8 degrees of subcooling going into the expansion device, saturation here at the evaporator, superheat at the outlet of the evaporator, and now what do we got here? Now we have measured temperature of 60, but we're at 67. 67 we said was 39 degrees. And the measured temperature is 60, so that means we're 21 degrees superheated. So we've got 21 degrees of superheat going into the compressor. That should be a pretty good running system. If any of these things, if a guy goes around, if your contractor goes around and takes these readings and writes them down, we've got some charts that are available that you can give to your guys. But they're going to be able to troubleshoot that system just from these numbers. So I hope that makes sense for you. So a lot of what this is about is what the contractor is facing out there in both installations, troubleshooting, all this stuff that he has to do to give the counterman, the wholesaler, the knowledge to be able to see what that guy's doing. Like if he comes up to the table, up to the counter, and he sets down some elbows, some copper elbows and some couplings and stuff like this, you visualize what this guy's going to be doing. He's going to be putting something together. He's got to braze it together. So you've got to ask him, does he need nitrogen, oxygen, acetylene, solder, flux, these kind of things. Mentally get into what this guy's doing. And that's a lot of what this class is about, is just showing what the tasks are so that you understand better how to serve your contractor. Okay, so we're going to talk about spatial location, condensing unit rigging, expansion valve selection, those type of things. Field wiring, some of that, typical wiring diagrams for defrost. Of course, line sizing, yeah, it's going to be into piping and brazing practices, that kind of thing. So when you're installing a condensing unit, If you're next to a wall, you want to have at least the width of the unit away from the wall so that it can have free air to breathe and you get no recirculation. When you have multiple units, you want to make sure that they're at least the width of the unit apart so they don't, so that the condenser air doesn't go from one to the other. If you're in a pit, down in the pit, the airflow, you might have to put a stack on here to get the airflow up above the pit so that it doesn't recirculate back down and around and into the side of the condensing unit. That will tend to make the head pressure too high. If you've got decorative fences, okay, like chain link fences, that kind of thing, you know, that have at least 50% free area, just one width of the unit away from those walls is all you need. But here's some shots of, you know, bad equipment placement. Now, just feature trying to change a compressor in that, you know, plus the fact that you can't get any air through it. Here's another one. Of course, this is kind of strange to me when you look at this, these condensing units. You know, this is outside, you know, like a 7-Eleven type place, some type of convenience store, gas station type thing. Those things would have been cut off the wall and hauled away by now. But you know, they're putting their shelving, just leaving the shelving against there, so water doesn't puddle on them, you know, that kind of thing. That is just asking for a big bill. Now this one, from Yakima, Washington. You can't even find the liquid line on this guy, but I think it was pretty great that they used the crates that the condensing units came in to make the rack that they're sitting on. So installing unit coolers. When this task is tackled by the contractor, the air pattern that you've got with the unit cooler has to cover the entire room. You never, ever put the evaporator over a door. And the reason for that is that if you put it over the door and it's drawing that warm, moist air from outside, whenever that door is open, it's going to freeze up, and it's going to freeze up prematurely. You're not going to be able to have enough airflow to take care of the whole room. So you've got to take into consideration where you're going to put that evaporator. Location of aisles and racks, you know, that are going to be going into the walk-in. If there are any, then you've got to figure that out. And the location relative to the condensing unit is important too. You don't want a condensing unit that's way over here and an evaporator that's you know, in the walk-in box when you can have the condensing unit closer. It keeps your charge smaller and it makes it run better. How are you going to locate condensate drains? If you've got a condensate drain coming out of a walk-in box in the middle of a room, where are you going to take that to? And we're going to look at some other basics too. So when you look at evaporator placement like this, you blow in at the door. That kind of keeps the warm, moist air from coming in through the door. Got some other shots of that too. If you have doors on the side here, you know, you've got a couple of different evaporators, you know, to blow sideways across them, that's fine. Then a couple different ways, different means of putting the evaporators where they overlap like this, or center mount them and blow against the wall and down. This would all be predicated by what kind of packaging you've got inside there, how they're stacking their stuff, the aisles that they might have is all, that's part of this. So when you have glass display doors, you want to blow at the glass display doors just to keep that the moisture off the inside, the condensation, that kind of thing. But you don't want to blow out through the door. And so you're showing here, it's shown here to use a baffle to blow that air. If that air is coming out of there, it'll blow it above the door and drop down through there, washing the surface of the door and taking that moisture off of it. So medium profile and large unit coolers. This is warehouse type situation where you got one unit cooler, at least half of the width of the unit away from the wall, and half the width going the other direction too. When you have two unit coolers, basically you've got 1 times the width in between those coolers, and then half the minimum of half the width on the other sides. Low profile, like your AA series, they're talking about 1.5 times the height when you mount those, so that away from the walls and away from the back wall. And the same with 2 unit coolers over here, 1.5 times the height on the side, and in between them, 3 times the height in between the 2 coils. Then the center mount. Now, center mount coils are like cutting room type coils. And at this point, I should ask, does anybody know what the proper temperature is for a meat cutting room? It's the temperature at which the flies slow down. So, you know, that'll help. Evaporator placement, 1.5 times the height from the wall, gives you enough room for return air. What we're trying to do, we're trying to get that air to go down here so that the product can reject its heat to it. So we've got enough air circulation going around through here. Then 1.5 times the height from the side walls, and of course that's the length there. That evaporator placement should be trying to get so it blows down through the aisles that the product's in, or be able to get down and around it so it can pull that cold, the BTUs out of that product. This is not acceptable, although it happens all the time, and you know that's how we sell compressors. But you know, stacking things up underneath there to where you have no return air coming back through here. When you slow down that return air, you get a freeze-up problem like this. You'll see ice banding and some real problems. So common sense has it that when you're doing this kind of thing, you gotta be able to blow around the product and back through and up into the return. So it's got to be set up that way so that you can get the product off the floor and away from the far wall so it can get around it. If you've got a blast freezer or blast cooler, having a turning vane keeps things sped up. It keeps from slowing them down because then you've got that corner there. It slows the airflow down. And possibly you might need some fans to blow through that product to blast it cold. So anyway, that's where we get to where Mr. Steffens is going to take over. And I'll try to escape out of this. I want to get over to Mr. Steffens, correct?
And Ed, you have been unmuted.
Yeah, okay, thank you. Let's see, where are we? All right. All right, here we go. Let's talk about distributors, coils, evaporators, and
Ed, you're going to need to share your screen.
oh, it's not? Oh.
I'm not seeing it.
Let me try this.
There you go.
There we go. Now I feel better. All right, sorry for the delay. All right, let's talk about distributor nozzles and expansion valves and how they relate to each other and how they work and such. Sizing and selecting. Commonly, we will see two different types of nozzles or distributors out in the industry. The Venturi type. Again, White Rogers, the old Alco product line, we used to manufacture the Venturi type, and we sold that product line a while ago to a manufacturer who actually still continues to manufacture the Venturi style distributor. There's also a nozzle type, which is what commonly you'll see with the Sporlan components and stuff. But the Venturi type, the way that this works is as the liquid is entering into, let's back up. Why do we need a distributor to begin with? Here we take a look at this coil right here. We got 1, 2, 3, 4, 5 different circuits in this evaporator that needs to feed, right? So what this does is the distributor helps distribute the refrigerant, liquid refrigerant, into the evaporator, actually saturated conditions into the evaporator to be distributed. If this evaporator per se was just one circuit, we'd have a lot of refrigeration down on one portion of the evaporator and the rest would starve. So for the most part, what we've done is we circuit that out, and we have 5 different evaporators, pretty much, if you want to call it that, 5 different evaporators or circuits inside the main body of the evaporator to help distribute the refrigerant. And so we have these distributors that are used to help do that. And so the Venturi type distributor, again, we talked about this the other day, creates about a 15-pound pressure drop across the distributor itself. And if you take a look inside here, it's got like a raised section here on both sides of the distributor. Now, internally, it's all the way around the distributor, right? So as the liquid comes in, what happens is the refrigerant in your expansion valves right here, your refrigerant tends to speed up. As it speeds up, the velocity speeds up, it tends to want to hug across this raised area of the distributor, and as it hugs this area, by the time it gets to this side of the distributor itself, internally, then it helps distribute the refrigerant down into the evaporator. All right. So what we would, this is a fixed size. That's one of the downfalls with this type of distributor. If this was incorrectly sized or so, you would have to change out the entire distributor. And we'll take a look at the nozzle in a few minutes and stuff. But what you would need for sizing and selecting, the information you would need for sizing and selecting this distributor would be what type of refrigerant you're working with, the application, is it a freezer, is it a cooler, what are the temperatures you're working with, and also the capacity. And then we'll be able to size and select the distributor. Now remember, if you ever have, I've seen this done before, where we've had to change out the distributor. Unfortunately, when we received a package unit with the evaporator and stuff, the manufacturer, now this never happens, right? The manufacturer sent us a system with the wrong distributor on it. So we actually had to change that distributor out. Now this is all one system too when sizing and selecting the expansion valve along with the distributor and the distributor tubes, right? The distributor tubes create a pressure drop as well, okay, along with this area right here. Now the nozzle type distributor that Sporlan manufacture, internally there's a little cone, and this nozzle itself actually sits into this raised portion of the distributor. Okay, it just kind of sets in there, and there's a retainer spring that holds this in place. Now the G corresponds to the distributor type, whatever type that distributor is. And you look at the different models that they may have, maybe like a 11, 28 or 25 or so. This nozzle actually fits into the orifice right here, or the inlet portion of that distributor. And then the 5 here, that does not necessarily mean or fall or correspond with capacity. That's just the size of the orifice itself, right? There's a couple, can't see it right here, but there are a couple, and I forget the size of the screw that actually fits in. You can put the screw inside there, and once you pull the retainer ring out, you can actually pull the nozzle out of the distributor if need be. And that's the advantage that you have with this style of distributor, is if there is a wrong or an incorrect nozzle within the distributor, then all you have to do is just change out the nozzle itself, right? It makes it a little bit easier. You don't have to change out the entire distributor. So again, a little bit more flexible. And you see this style more common in refrigeration applications than I personally have with the Venturi, but they are out there. Now the pressure drop across this distributor assembly, along with the distributor tubes, is anywhere from a 25 to 35 pound pressure drop on this assembly right here, okay? And again, that's depending on what kind of refrigerant you're using. I believe ammonia is 35, and for the most part, everything else is pretty much around 25. But if at any rate, if you have any questions, you can refer to the literature that's provided. So sizing and selecting nozzles, again, we need to know the refrigerant, the suction temperature. It's almost like a common theme for sizing expansion valves and all this. These are pretty much all the criteria that's required for sizing and selecting all the components. Then we need to know the ID of the distributor, capacities and the evaporator temps, liquid temperature. Remember, liquid temperature for 404A, if it gets down to 50 degrees entering temperature, your capacity at the expansion valve can go up to 1.5 times that normal rating. So instead of having, again, a 10-ton expansion valve on a system, you could have a 15-ton expansion valve on a system, and you could overfeed and possibly slug back during low load conditions and stuff. So that's important. Again, and then the pressure drop that's required across the nozzle itself. Again, a lot of this information is available in the catalogs. So preferably, I like to see where the distributor is in the vertical position, right, where the liquid refrigerant leaving the expansion valve actually comes down in the vertical plane, so that it feeds all the distributors, the distributor tubes evenly. Okay, pretty much the same thing with what you see here. However, you do see some of the distributor nozzles or tubes here. Some of are feeding and some of them are not, and that could be because of this, the way you have this setup. It's recommended that I personally like to see the expansion valve close coupled to the distributor if at all possible. Here we have the expansion valves somewhere over here, and then you have a U-bend, a 90-degree elbow here feeding the distributor. So portions of the distributor tubes are being fed, and then half of the distributor tubes looks like they're not being fed. So you have unequal distribution through the evaporator, and that could be a huge problem for efficiencies and stuff. All right, we're going to talk about expander valves, one of my favorite topics besides compressors, right? So again, expansion valves. Take a look at this real quick. This is an internal equalized expansion valve, right? And you have the evaporator pressure that right here, internal equalized expansion valve. This force from the evaporator pressure tends to want to push force underneath this diaphragm. Let's back up here and start all over. Here we have the power head assembly with the bulb. The bulb attaches itself to the other side of the evaporator, right, and it senses temperature. But what we're trying to control with the expansion valve is superheat through the evaporator. And this whole I call it a system, where we have the bulb attaches to the power head itself. It's all pressurized, okay? So that's one of your opening forces. This force right here pushes from the diaphragm, and then you have the diaphragm follower and everything, and it pushes down on this pin whenever it's warmed up to allow more refrigerant to pass through the expansion valve into the evaporator, okay? So along with this force here, the bulb force or the pressure is the liquid. So we got the liquid and the bulb act as combined as a force, right? That force is trying to push this valve open. Opposing these two forces would be the evaporator pressure that's trying to close the valve, because it puts pressure underneath the diaphragm, and then we have the superheat spring right here. And this superheat spring is the only portion of the expansion valve that's adjustable, okay? And we adjust it to whatever superheat setting we want to maintain at the evaporator. I used to have a rule of thumb. 10 degrees was pretty good. When I was back in with Sporlan back in the 90s, we used to throw out 10 degrees as a good rule of thumb number. But if you take into consideration the lower your suction temperature is on the evaporator, you could drop that down quite a bit, actually, 6 degrees, sometimes even 4 degrees superheat. The less superheat you have at the expansion with the expansion valve, the more refrigerant we have feeding the evaporator, and our efficiencies go up. However, at low load conditions, and we talked about load the other day, at low load conditions, if our expansion valve is oversized, we could possibly flood back to the compressor and create some flood back, like as per what Kevin talked about. Now this, being that this is an internal equalized expansion valve, we want to use this expansion valve for systems or evaporators that have no pressure drop across the expand. Well, obviously you're going to have some pressure drop, but I'm going to include the fact that we don't have a distributor, no distributor nozzles or anything like that. A pressure drop, really anywhere from 1 to 3 pounds across the evaporator. This would work just fine. This type of internal equalized expansion valve. The external equalized expansion valve, what we're doing here is we're actually plumbing this external line right past the bulb location where the bulb is actually attached to the suction line, okay? And what we're doing here is, if we had an expansion valve in the system where it was an internal equalized expansion valve, and we install this on a system that has a distributor, that 35 pounds actually is seen underneath the diaphragm right here, and it actually causes the expansion valve to want to close. This is if we're installing an internal equalized expansion valve on a system that has a distributor, right? So that 25 pounds actually pushes underneath this diaphragm, which causes the valve to want to close up, and we actually starve the coil, and our efficiencies in the evaporator is greatly reduced. So in that case, we install a TXV that has an externally equalized expansion valve, and then again, this is plumbed downstream where the bulb is located, and we no longer see that additional 25 pounds wanting to try to close up this valve to starve the coil. So that is our that's our review with the expansion valves. Again, I always say replace like for like if you can. If you have an expansion valve that is internal equalized, you can replace it with an external equalized expansion valve. If you have an expansion valve that is a balance ported expansion valve, make sure you replace that valve with balance ported and not a conventional expansion valve. There's a reason for that. We don't talk really too much about power heads and how power heads, you know, the charge in the power head and the element and everything. We don't talk about that too much here. With an expansion valve that has an MOP feature, like a HW65 or something like that. But we do have literature that can support that. If you have any further questions or want to take a look more closely into that, we do have literature that you can use to find out what an MOP is, a pressure limiting expansion valve. So we're going to go through a real quick selection here. I like this selection here because it kind of throws a curve in here. I always size the expansion valve to the evaporator capacity, right? I've always done that, and not size the expansion valve to the compressor. So here we have a system that has one condensing unit rated at 24,000 BTUs or 2 tons. R404A is a refrigerant, and we have here we have two 10,000 BTU evaporators on the system. So we have one condensing unit that's feeding two 10,000 BTU evaporators. And if we take a look at this, we're going to be oversized, right? With the not necessarily greatly oversized, but our condensing unit can definitely serve the purpose for the two evaporators. But what we've done here is we have what we call the balance point on capacity for the system, where the evaporators, if we take into consideration at a 10-degree temperature drop, our evaporators could be rated at 10,000 BTUs. But if we take a look at a 12-degree temperature difference between the evaporator and the space we're trying to cool, our capacity actually goes up a little bit on those evaporators. So in that sense, we now have two evaporators that are balanced to the condensing unit itself at a 12-degree temperature difference rated. And those ratings are also in the, if you look at the evaporators, you have that, those ratings are available and stuff. So now we size the expansion valve at 12,000 BTUs. Right? So taking into consideration that we're using a 150-pound pressure drop across the expansion valve, some of the bulb locations, and bulb location is very important when you're laying out your system and stuff. I always want to take a look at the fact that where's the airflow in relationship to where the bulb is being located, and especially after you locate the bulb, make sure you insulate the bulb and stuff so that there's not any outside disturbances or different temperatures that could play on the total operation of the bulb itself. For instance, when I first got hired on with Copeland, I actually went out to a job site, and then this one company, they were losing 60 compressors every winter. And when I asked the guy, the contractor, I said, well, can we see let's take a look at the bulb and see what's going on here. So again, they would lose these compressors with slug conditions, and slugging back to the compressor and everything on low load situations during the winter time. And what we did is we actually were able to break into the cabinet, cut a hole in the cabinet, and take a look at where the bulb was located, and the bulb was actually flaying or floundering in the airflow, and it was getting a sense of the air temperature and not necessarily the superheat which is what we're trying to control here on the leaving side of the evaporator. and come to find out even further that they use zip ties to install the bulb onto the suction line, and that in and of itself is a no-no itself, right? So again, bulb location is very important. Also, if you can insulate that, make sure that that gets insulated so we only sense the temperature of the bulb and not necessarily what's happening in the airstream itself. Also, the location, this bulb is located at the 12 o'clock position here. It's not being affected by either the liquid refrigerant and or the coldness of the oil coming back that's being pulled at the bottom of the tube itself. This is just an exploded picture of that. So depending on your, if it's a horizontal location or a vertical location where the bulb is located, again, we're using copper straps to strap the bulb onto the suction line, and that's the best way to install the bulbs if you can. A lot of I know our White Rogers, our expansion valves come with copper straps, brass straps, copper straps to strap on the bulb to the suction line. Better conductivity with the copper, and it's just a better strap altogether. Here we're taking a look at on the vertical side where the bulb is attached with the capillary tube feeding down into the bulb itself. There's a lot of controversy with that in the sense where people say, well, it's best that you have the capillary tube on the top of the bulb rather than where the capillary tube actually goes on the bottom. I prefer having it on the top, even though some of the manufacturers, the capillary tube actually extends a portion inside the bulb itself to where you can locate it either with the capillary tube up or the capillary tube down. But I'm old school, so I tend to like to stay with what I've been taught throughout the years. And I personally like to install it with the strap, with the bulb and the capillary tube at the top. See where are we with time? 9:18. Here's another picture of the bulb. Again, it's located at the top. Again, we got this airflow, right? This is a coil, but we got this airflow going up. Could hit this, you know. Again, I would probably insulate that, keep that away from the airflow. There it is. We took that one step further and we've insulated and stuff. So I knew that was coming up. Here's the vertical position. This is kind of cool. You actually got the distributor. There's the expansion valve right here. You got the distributor, the distributor tubes feeding the evaporator, and then come back here. This is your external equalized line, probably a 1/4-inch tube that's actually brazed into your suction line. Here's your bulb, and then you have your suction header. Again, depending on what size of line that you're working with, will determine the location, the best location for the bulb itself. Anything under 7/8, probably the best location for the bulb, I would think, would be the 12 o'clock position. Again, and the reason for that is because on the gas coming back, the refrigerant coming back from the evaporator, you're going to have a little possible pool of liquid of oil down here at the bottom of the suction line, and that could create a false reading if our bulb was located down at the bottom. For anything, for our lines 7/8 up to 1 5/8, it's recommended the 10 or the 2 o'clock position, and anything greater than 1 5/8, you can locate it at the 3 and or the 4 o'clock and the 9 o'clock position. You know what? I think this might be a good spot. Should we take a break? We can probably go. We won't talk about the liquid line solenoid today. We talked about that the other day, unfortunately. But I always make sure that the liquid line solenoids, or any solenoids in particular, are there's an arrow flow at the bottom of the solenoid valve. So always make sure that the direction of the solenoid is in the direction of the flow with the system itself. Also make sure that you size and select your solenoids with the capacity charts, not necessarily the nominal ratings on the side of the box. And there's a reason for that. If you oversize, sometimes you can. I've seen this happen where guys have oversized the solenoid valve to the line size and not necessarily to the capacity that they were working with, and they've had some hammering conditions there with the solenoid. So make sure you size your solenoid. Okay, and then we'll talk about a little bit. We're going to brush up on head pressure controls again, filter dryers. I don't think we talk too much on that. A little bit on lubricants, heat exchangers, and oil separators and suction accumulators. And I think this might be a good point to stop.
This is a good place to stop. We can certainly do that and give everybody about 9 minutes back of their morning. Again, thank you, Kevin and Ed, for presenting today. We will pick this up again tomorrow at 11:30 Eastern Time. I would encourage you, if there are any questions, you can send them in to me, or you can post them to the chat. That's one of the options that's on the screen, and I will feed that information to Ed and Kevin as we go through. But thank you, everyone. Have a good day, and we'll talk to you tomorrow.
Thank you, Julie.